Yeah. So you are able to, within a matter of seconds, you will be able to establish equilibrium. If you have Excel spreadsheet laid out, all that you have to do is go to data, then go to what if analysis, so first thing is go to data analysis, then what if scenario, and then third is goal seek. You try a couple of times, you will learn that. Very, very simple. And I use in almost all my spreadsheet, I use goal seek. Wherever I need to do strain compatibility method, just establish this sheet once, have your goal seek entered in one of the cells, click goal seek, you get your answer within a matter of seconds. Okay? So that's how you need to do for under reinforced sections. All right. So I don't have an example. Normally I do for my graduate students, but I don't have one. But I'm sure you will be able to develop your own sheet if you understood the process. Is this clear to all of you? Very good. Okay, so we'll now move on to, if you have any questions, this is a good time to ask questions. If not, we will move on to the next item, which is strain compression. Yeah. Okay, so serviceability design. Okay, now we are going to address serviceability design. Okay, so until now we talked about strength, movement strength. Now we are going to talk about serviceability. In case of FRP reinforced beams, there are two things that we check normally: crack widths and deflections. Crack widths and deflection. These are the two things we'll check. We'll also check creep rupture stress, but that's at a later stage. First we'll start with crack widths and deflections. So generally speaking, we all understand this really well. We know that the stiffness of FRP reinforced beams is slightly, not slightly, but it is smaller than steel reinforced beams. Therefore, you will have cracking, significant cracking and large deflections. And many times your deflections may govern your design. It's quite possible. So cracking is mainly for appearance, right? Aesthetics. Water tightness is important in some cases, like water tanks. Water tanks anyway, they don't want you to have any cracking, mostly. And in some cases, and creep rupture is also going to be a problem. And in case of shear, already it was mentioned, dowel action is a problem. So we will talk about that later in shear design. And we need to limit our deflections to make sure that the partitions don't crack. There is no excessive cracking in non-structural elements. For that, we need to limit our deflections. So ACI 318, of course, IS 456 also has the methods for deflection calculations for beams, right? We know that. However, because of the relative stiffnesses of steel reinforced concrete beams and FRP reinforced concrete beams, there is a difference, and therefore if we use the methods given in steel reinforced concrete beam codes or specifications for FRP reinforced beams, it may not work. In most cases it will not work. So we have to make some adjustments. All right, that's what we are going to do in next few minutes. So if you use steel deflection calculations for FRP deflection calculations, you will always underestimate the deflections. Okay. So for cracking, what are the considerations? Cracking is mainly important because any cracking will create some access to environment. For steel reinforced concrete, that's a big deal. It's a big problem. So for corrosion resistance, you want to keep the cracks tight. And for FRP, that's not necessarily a problem because FRP is not, it doesn't corrode by itself. So you can tolerate crack widths that are slightly larger in case of FRP bars or beams reinforced with FRP bars. So there are two methods. One is to find out the actual crack widths, calculate the crack widths, compare them with maximum limits. That's one option. The other option is to place your reinforcing bars close enough that the cracking is controlled. Okay? So I think I may be wrong, please correct me if I am wrong, but IS 456 is still asking you to calculate the crack widths, right? But in ACI code, they are actually not asking you to calculate the crack widths anymore. What they are saying is they are specifying bar spacing. They are saying don't place your bars at spacing greater than the maximum allowed for crack control. So there is an equation that we can use to find out the maximum spacing of longitudinal bars, not transverse bars, longitudinal bars in the direction of the beams. So if the spacing is less than the maximum specified, we assume that crack widths are under control, which is not true, but that's a different issue. That's what ACI says. And those are of course based on some limiting values of crack widths. Japanese code will limits it to 0.02 inches, which is 0.5 millimeter. Canadian code says 0.5 millimeter, and other codes are for aggressive environment, and for other environments it's 0.7 millimeter. And ACI is based on 0.46 millimeter to 0.56 millimeter. So there is a basis for the maximum spacing of longitudinal bars. It's not just baseless, but it is based on some things. But that's not working. If somebody is interested in doing any research, that's a good research to work on. And those limits are not adequate in most cases. And in some cases, of course, we don't want to go there, but if you use those equations, in some cases you will find maximum spacing which is a negative value. How can I have a maximum spacing which is negative? You cannot, right? But anyway, that's the limitation of that equation. So those of you who are familiar with crack width equations, IS 456 is based on this actually. It's based on this equation. The original equation was suggested by Gurgley and Lutz. This Gurgley equation is very famous. It was developed in 1960s or something like that. Nobody has changed that until this point. So then they used to give this crack width equations in the ACI code and Canadian code and all other codes. It's in US units. And then they used to give a maximum crack width limits. This is the actual crack width, and then there are limits. So anyone who is not even an engineer can compare the two. Actual crack widths versus calculated crack widths. Maximum crack widths and calculated. So in many designs, the designers were not paying attention and they used to allow larger crack widths than this. So the crack widths calculated using this equation worked out to be larger than the limits. And then somebody used to catch and they say, oh, your crack widths don't conform to requirement, so your design is rejected. So they tried to hide this. They had a Z factor. I don't know you guys are, I don't know if you are familiar with Z factor. There's a factor called Z. That's called crack width factor. For a few years they used that. So Z factor is something, or Z factor is something that everyone cannot follow. Just looking at it, you don't know what Z factor is. It is 150 or 200, whatever that factor is. Nobody knows what the basis is other than those of us who actually know the basis. So they tried to do that for a few days. That didn't work. Now they are gone to this spacing requirement. Even that's not working. So let's not worry too much about what's not working. But the actual equation in ACI is this equation here. Spacing, maximum spacing in SI units is this one here. Should be less than 380 times 276 over Fs minus 2.5 cc. Cc is the concrete cover to the bars closest to the surface. Closest to the surface. That's what cc is. And Fs is the service load stress in the bars, which is approximately what? What do you expect your service load stresses in bars? So IS 456 also would have mentioned that. It's 65% or 67% of Fy. That's your service load stress in steel normally. So you can plug in Fs equals 0.67 Fy and then come up with the spacing equation. So as long as your spacing is less than what is given by this equation, there are two equations actually, one here, one here. Use both equations, pick the smaller value, and that's what is your maximum spacing. If you place your bars closer than this maximum spacing, you're fine. If not, you should change the diameter of the bars, reduce the stress in the bars by adding more bars than required for flexure. That will work too. So FRP reinforced concrete also is based on similar approach, where S max is equal to 1.15 EFW over FFS KB minus 2.5 cc. Once again, cc is the concrete cover from the center of the bar, edge bar or any bar, to the nearest face of the beam, nearest face of the beam. So cc is defined as the concrete cover to the center of the bar to the nearest face of the beam section, and then kb is a bond related coefficient. If your FRP bars can develop as well as a normal steel bar, then kb equals 1. And of course, we don't expect our FRP bars, no matter how good the surface condition is, even this one here may not be able to give you same amount of development length or same amount of pull-out strength as steel bars. So we need to use a larger value than 1. Okay? So for now, until there is further research, kb is taken as 1.4. That's a conservative value. 1.4 is what we use for kb. EF is the modulus of elasticity of FRP. FFS is again the stress at service load. Here we will not use 0.67 FFU as the basis. We will not use that because in our over reinforced sections, our FF is always going to be smaller than FFU, right? In most cases, we will use over reinforced section, and that stress is always going to be less than FFU. Therefore, FFS is to be calculated. It needs to be calculated based on elastic analysis. So we need to find out FFS based on elastic analysis. And then your units are consistent. This is a ratio of similar quantities, no problem. Whatever is your unit of W and CC will be the unit of S max. And acceptable W is in the range of 0.016 inch, which is 0.4 millimeter to 0.7 millimeter. So if you are exposed condition, use 0.4 millimeter. If it is not exposed, it's a protected condition, use 0.7 millimeter. Of course, you can use your own judgment to use a different value, which is allowed in ACI 440.1. So the equation itself is generally valid if this expression is satisfied. If DC is less than EFW over 2FS beta KB, then it's fine. We can use that other equation, this equation. Okay? If this condition is not satisfied, then we have to use a larger value of DC. Again, DC is the depth of the concrete cover. Depth of the concrete cover. It's not same as CC. CC is distance from the center of the bar to the nearest surface. It can be side distance or bottom distance, whereas DC is concrete cover to the bottom. Okay, so we can increase DC or reduce stress FFS by providing more number of bars, larger number of bars, or increase the area of FRP bars. Okay, so some notes on crack widths. So limiting crack width depends on intent and application. We know that, that's common sense. Maximum value is between 0.4 and 0.7 millimeter. Service load stresses can be determined using cracked, elastic, transform section. Cracked, elastic, transform. 3 items. Cracked, elastic, transform. 3 items. Sections. So use moment of inertia based on cracked, elastic section modulus. Transform section modulus. K sub B is 1.4. That's what we will use. Then we have crack widths under sustained loads can be 40 to 60% larger than under short term or transient loads. That's something I think somebody was talking about, sustained loading and cracking. One of you, PhD student. So if you have sustained loading, the crack widths will always be larger, for sure. Okay. So now the next item is deflections. How much time do we have? Another half an hour? Okay. So in case of deflections, for steel reinforced concrete, we have 2 methods. One is you can find out the actual deflections using deflection equations, number 1. Number 2, if you satisfy the minimum thickness requirements for slabs and beams, then you assume that the deflections are within the limits. Right? Do you remember that? 2 approaches. One approach is to find out the actual deflection based on cracked transformed section properties and or what's known as effective moment of inertia. Calculate the actual deflections based on effective moment of inertia. That's one approach. The other approach is simpler approach. If there is a table or 2 tables for minimum thickness of the element, one for slab, one for beams. So if my thickness, minimum thickness for deflection control is greater than what is given in the table, then we are okay. That means the deflection need not be checked. That's the easier option. For reinforced concrete, steel reinforced concrete,